Alright, so welcome to a new chapter. This is a chapter on alkynes. In this chapter, you may feel a bit of deja vu because alkyne chemistry is very similar to alkene chemistry. We will break this chapter into two parts. In this video, we will introduce alkynes and their nomenclature. Then we will talk about the acidity of terminal alkynes. Lastly, we will start with the first reaction of alkynes, the reduction of alkynes. So moving away from alkenes, we are now going to alkynes. So adding another pi bond to the carbon-carbon bond. Alkynes are not as prevalent as alkenes, as in they are not as prevalent in nature or used in industry, but we do see them used for example, simplest alkyne acetylene in gaseous form when combusted is used in welding, or you can see the alkyne moiety in various drugs, as we will explore in a bit. Like I just stated, acetylene is the simplest of the alkynes because it has only two carbons, and at the end of each carbon is a hydrogen. So we will use this simple alkyne to explore the properties of this functional group and its reactivity. The triple bond is actually composed of one sigma bond, the head-to-head overlap of the sp orbitals, highlighted here in gray. And then there are two p orbitals that are orthogonal to each other. One set of p orbitals overlap to form one pi bond, and the other set of p orbitals will overlap to form the second pi bond. So in a triple bond, in a alkyne functional group, you will have a sigma bond and two pi bonds. Because of these 6 electrons between the two carbons in the alkyne, the electron density is located between these two carbons. Highlighted here in this electrostatic potential map, you see that the red region is between the carbon and the carbon of the alkyne. So because of this electron density, because of the pi bonds, the alkyne chemistry will be very, very similar to alkene chemistry. So in this chapter, we will see a lot of overlap and review from the alkene chapter. Now back to the introduction of alkynes, where you can see them in industry and nature. And as previously stated, alkynes are not as prevalent in nature as alkenes are. And in fact, alkynes have been isolated in more than 1,000 compounds in nature. One of such, for example, this compound here, histrione cotoxin, is a compound found in poisonous frogs from South America. Now, jumping into man-made molecules, the alkyne functional group is found in this oral contraceptive, ethinyl estradiol. A key feature of the alkyne functional group is that it is very rigid. Because of the triple bond, the geometry of the alkyne is linear, so there's no bend. And because of pi orbital overlap, there is no rotation of the bonds. And so when organic chemists try to add rigidity to their molecules, they will often look towards to the alkyne moiety. Okay, so let's talk about how to name alkynes. Alkyne nomenclature is very similar to alkene nomenclature, which is also very similar to alkane nomenclature, except with these modifications. First, you have to identify the parent chain, which now should include the carbon-carbon triple bond. Then you identify and name the substituents. That's not anything different. Third step is to assign the locant to each substituent, giving the carbon-carbon triple bond the lowest number possible. So whichever end you start out with should give the carbon-carbon triple bond the lowest locant number possible. Then, just like the alkane, you would list the number of substituents before the parent name in alphabetical order. Then lastly, the triple bond locant is placed either just before the parent name or just before the YNE suffix, the "-ine" suffix. Okay, so we'll go over this now. So first is to identify the parent chain, which again should include the triple bond. So here, for example, if there's a 5-carbon chain, we call that a pentane. And if that 5-carbon chain has a double bond, we call that a pentene. And if that 5-carbon chain has now a triple bond, we just call that a pentyne. Taking a look at this example here, notice that the longest continuous chain is composed of 8 carbons. So we would highlight it in red here as the parent chain. So the parent name would be octane, right? And the 2-carbon chain is considered a ethyl substituent, right? However, if that ethyl substituent is now a triple bond, it will now be the parent chain because again, the parent chain must include the alkyne. So even though it's shorter, only 7 carbons, it is considered the parent chain. And so in this case, it is the heptyne as a parent. All right, so that wasn't different from your alkene nomenclature. And step 3 is a little bit different too. So when you assign a locant, you want the triple bond to be seen first. So for example here, you wouldn't number it from right to left because the alkyne is seen as the 5th carbon, as opposed to when you number it from the left to the right, the alkyne is seen at the 2nd locant. So 2 is lower than 5, so the correct way would be the one on the left. Alright, so having all that, let's put the name together. Notice that we have substituents here at carbon 5 and carbon 6. They are all methyls. So we will say 5,5,6 trimethyl, because there's 3 methyl, 2-heptine. Okay, so that's the first way where you put the locant of the triple bond 2 in front of the entire parent name. Or this other way is you put that locant number 2 in front of just the YNE, the ine. So it would be 5,5,6 trimethylhept 2-ine. Alright, so let's name this compound for practice here. First, let's find the longest chain. That includes the alkyne, which will be these 10 carbons here. Next, you will decide which end you will start numbering the locant as number 1. In this case, if you count it from this end here, you will see the alkyne at carbon number 3, so that would be the earliest. So this is the correct numbering system. So that's the complete of the locant. Now let's find the substituents. You have one substituent here at number 5, and it is an ethyl. And you have 2 substituents at number 7, both being methyls. So now let's assemble the name, putting the substituents first in alphabetical order. E comes before M, so the ethyl group will be named first. The locant of the ethyl is number 5, so that's 5-ethyl. And then now the methyl group. Since there's 2 methyl groups, we have to name both of them. So 7,7-dimethyl. Alright, so there's nothing else. So now we're going to just name where the alkyne is. It is located first at carbon number 3. And now there's 10 carbons, so dec, so decyne. Or you can put the 3 just in front of the ine. It can also be named 5-ethyl-7,7-dimethyl dec 3-ine. And what happens if there's multiple functional groups in your compound? Well, as you can see here, this is the chart of priorities of functional groups according to the name. So anything that's numbered first will have priority as a parent. As you see here, alkene and alkyne are way at number 12. So if there's nothing else basically, then they will be parent chain. But if there is something else, like an amine or even an alcohol, those functional groups will take priority. In terms of alkene and alkyne, they actually are a tie. They are equal in priority when you are counting locant, but the alkyne will always be the last name, the ending name. So for example here, if you have a 5-carbon chain and you have a triple bond between carbon 1 and carbon 2, a double bond between carbon 3 and carbon 4, you would name this pent, and then 3 is where the alkene is, right? So pent 3-ene 1-ine. 1 is where your alkyne is. And so because when you count from the left, you see alkyne as number 1. When you count on the right, you will see alkene as number 2. So whichever you see first will be your locant numbering system. So in this case, we saw on the left-hand side, the functional group alkyne first. So you start 1 from the left-hand side. All right, now let's see this example though. What if there's a tie? As you see, if you count from the left-hand side, the alkyne is seen first at number 1. And if you count from the right-hand side, you will see the alkene first as number 1. So there's a tie there. So when there's a tie, you just start numbering from the alkene. But keep in mind that the alkyne will still be the ending of your name. So in this case, this one is called pent 1-ene 4-ine. Okay, so again, 1-ene because the alkene is seen as carbon number 1, and the alkyne is seen first at carbon number 4. Alkenes also have common names that are derived from its most basic form, the acetylene. So for example, if you have an acetylene with another methyl group instead of a simple hydrogen, we call that methyl acetylene. Or when you have 2 isopropyl groups on both sides replacing those hydrogens, we just call this common molecule diisopropyl acetylene. If there are different substituents replacing the hydrogen, we can just name them one at a time and in alphabetical order. So this one is phenylpropyl because there's a phenyl group on the left-hand side and a propyl group on the right-hand side. So phenylpropyl acetylene. And there are 2 types of alkynes. One is called the terminal alkyne, where the alkyne is at the end of a chain. So all terminal alkynes will also have a hydrogen connected to the carbon of the triple bond, as opposed to an internal alkyne, whereas the name states it is on the inside of the linear chain. So both carbons of the triple bond are connected to another carbon instead of a hydrogen. At this point, let's go back a bit and talk about that terminal alkyne because they do have special properties. We will start by discussing its acidity, then we'll pause there, and then we'll save it until the next video when we'll talk about how useful it is when it comes to synthetic strategies. If we were to compare the acetylene to its counterpart, the ethane and ethylene, we would remember the acetylene is much more acidic than its two analogs, with a pKa of about 25. So it's much more acidic than a normal hydrocarbon. And to understand the acidity, let's take a look at its conjugate base, the acetylide ion. So remember how to qualitatively judge whether a proton is acidic. When you remove that proton and therefore generating a negative charge, if that negative charge is stabilized, is happy in that conjugate base, then it will be a relatively strong acid. So let's compare the negative charge upon deprotonation from an alkane, the alkene, and the alkyne. Notice that the negative charge will now reside on the same carbon. So ReO is not going to help us with first term, A, atoms, right? Because it's all on carbon. The next term is R, which is resonance, and none of these has resonance. And then so the third term, induction, also doesn't help because none of these have induction. So there's the last term here in ReO is orbitals. So let's take a look at orbitals here. If you are a simple alkane, the lone pair resides in sp3 orbital. Remember, sp3 means it has more p character, 3 p's versus 1 s character, right? So it has more p characters, so it's further away from the nucleus. If it is on the alkene, then you are now in an sp2, now less p and more s, so it's getting closer to the nucleus. And finally, if you're a negative charge on the alkyne ion, you are in an sp orbital, so 50% s character, 50% p character. Because it has more s character in overall, it's closer to a nucleus. A negative charge next to a positive nucleus is very stabilizing. So because of this, that negative charge is the most stable among these three. And because of that high stability, this conjugate acid has a low pKa, so it's more acidic than a normal hydrocarbon. So now that we know the pKa of our acetylene, let's see what happens when it is in an acid-base reaction. Let's say you want to deprotonate it with sodium hydroxide, the OH. Would this be a good base to deprotonate our acid? Remember, in an equilibrium, the equilibrium favors the weaker acid and the weaker base, right? So what is the weaker acid and the weaker base? Taking a look at the acids alone, our pKa of acetylene is 25, whereas on the product side, the pKa of that acid is 16. The acetylene is the weaker acid, right? So this reaction actually favors the reactant side. So no, hydroxides are not strong enough to deprotonate acetylenes. So what is strong enough? So for example, here we have amides. So sodium amide will generate a conjugate acid with pK of 38, making it a weaker acid than acetylene. Because of this, the product side is heavily favored, driving this reaction to completion. So those are two examples of what bases can and cannot deprotonate an acetylene. Remember, you need a conjugate base of an acid that is weaker than acetylene, right? So you have here pKa's of 50, 38, and 35 are definitely weaker acids than 25. So if you take the conjugate base of those, you will have good enough bases to deprotonate acetylene. So you have a carbanion, an amide, or even a hydride. All of those will be strong enough to deprotonate your acetylene. Whereas all the alkoxides in the bottom there will not be strong enough to deprotonate your acetylene. Now let's explore what kind of base can deprotonate a terminal alkyne. I'll give you three possibilities. Tell me which one will be strong enough to deprotonate the terminal alkyne. So the first here we have is sodium acetate. The second here is butyllithium. And lastly, what we have here is known as lithium diisopropyl amide, or LDA. Which one of these is strong enough to deprotonate your terminal alkyne? Let's take a look at one case at a time, drawing its equilibrium. Okay, so in the first case, if the reactions were to proceed, you'll get a deprotonated alkyne, your alkalinide, plus your protonated base. Okay, in this case, you get an acetic acid back, right? So let's compare our pKa's here. Our pKa of the terminal alkyne is about 25. Do you remember the pK of acetic acid? It's around 5, right? So therefore, acetic acid is a stronger acid. So what does that tell us? That tells us that it's going to favor the reactant side, the weaker acid. So no, the sodium acetate will not be strong enough to deprotonate your terminal alkyne. All right, so let's do that again with our next one. And again, this was butyllithium, sometimes abbreviated as BULI. Butyllithium, once it is protonated, will become just a butane, right? And what is the pK of a butane? It's about 50, right? So comparing 25 to 50, which is the stronger acid? The 25. And therefore the alkane is the weaker acid, so it will push the equilibrium indeed towards the product side. So yes, butyllithium is indeed strong enough to deprotonate your terminal alkyne. And lastly here we have what we call LDA, or lithium diisopropyl amide. If that is protonated, it will form this compound. And what is generically what we call this compound? An amine, right? So what do we think an amine's pKa would be? Around 35? So comparing the amine versus the terminal alkyne, which one is a stronger acid? The alkyne is, right? So therefore, it's going to push the reactions towards the product side, again, meaning that the reverse reaction is smaller. So making this reagent also a good reagent to deprotonate your terminal alkyne. So the general trend is if your base is an oxygen, it's not going to be strong enough to deprotonate a terminal alkyne, but if it's a carbon or a nitrogen, it most likely will. Alright, so now that we know what alkynes are and some of their properties, now let's discuss how they can be synthesized in the lab. As you may recall, you can prepare an alkene via an elimination reaction when you have an alkyl halide with a strong base, right? Well, that reaction can also form an alkyne, it just needs to happen twice. So you need a dihalide and a very strong base to do 2 elimination steps. Okay, so here's the reaction. So your first step is basically forming the alkene via an E2 elimination reaction with a strong base, deprotonating the beta hydrogen and kicking out one bromine, giving us this bromoalkene. Now, if you have a second equivalent of that strong base in there, it can do a second elimination, again, via E2 mechanism. It will deprotonate the beta proton, forming the triple bond, and then kicking out the bromine atom, giving us our alkyne. So this is what we call a geminal dihalide, where both of the halogens are on the same carbon. You can also do this with what is known as vicinal dihalide, where the 2 halogens are on adjacent carbons. Again, you would need that strong base to do 2 rounds of eliminations. And so most often, the strong base here will be the amide. So the reagent will be sodium amide dissolved in ammonia. Hydroxide will only work in the first step, but it's not strong enough for the second elimination. So this reactions only will work with amides. And actually there is a second step, because as you obtain your final product, the terminal alkyne, remember that terminal alkyne is acidic, and if you are in basic condition because of amide is your reagent, it will deprotonate that terminal alkyne, giving you an alkalinide ion. An alkalinide ion is basically an alkyne that has been deprotonated. Okay? So this reaction actually requires a second step, and this second step is known as a workup step, where you simply add water so that you can do an acid-base reaction, yielding your protonated alkyne, your target product. Again, anytime you add water or slightly acidic water into a solution to obtain a neutral compound at the end, that's known as a workup reaction. Alright, so in summary, to form that alkyne, the steps are as following. You submit your dihalide with excess. The letter XS here stands for excess. I know, super punny. But yeah, that means an excess amount of sodium amide in the solvent ammonia, followed by a second step of workup with water. Alright, so take a look at this example problem here. If you had this dihalide and the following steps involving excess sodium amide, and followed by water workup, can you predict the product and also draw the mechanism? So the product would be an alkyne, right? Since on this side there's no hydrogens to deprotonate from, it must have deprotonated from the other side. Now when you draw this, just make sure you have the same number of carbons still. On this side you had 1, 2, 3, 4, 5, 6 carbon. On this side 1, 2, 3, 4, 5, and 6. So it is correct. Often a simple mistake students make is when they are redrawing the product, they are adding or losing a carbon because the alkyne kind of trips them over a bit. And also note that whenever you draw an alkyne, whatever's coming off the alkyne, whether the hydrogen or an alkyl chain, it must be linear. It must be 180 degrees because of the geometry of alkynes. So don't draw alkynes in a bent geometry. That will be a big faux pas and looked down upon. Now let's draw the mechanism. So remember there were hydrogens here, so let's draw in the hydrogen. And the base is this amide. It's going to do an elimination step, deprotonating that hydrogen, forming a double bond and kicking out one halogen. Okay, and this happens a second time in the second elimination step. Okay, notice that this is not the end if you were drawing the mechanism because we haven't even used that water yet. Remember there was an excess of base so that the terminal alkyne, a relatively strong acid, will not survive in this solution. So there will be a last proton transfer step. So you're actually using 3 equivalents of that amide. So this last step is your workup step where you protonate your alkylamide, forming your protonated terminal alkyne. In the last segment of this video, we'll explore our first reactions of alkynes, which is the reduction of alkynes. Recall back in the previous chapter when we talked about the reduction of alkenes, which is adding hydrogens back across that double bond. So analogous to that, the reduction of alkynes is adding hydrogens back across that triple bond. The difference now is that you don't just have one pi bond, but 2 pi bonds to work with. So let's begin with something familiar, the catalytic hydrogenation reaction. We've seen how to reduce alkenes in the previous chapter using hydrogen gas over a catalyst like nickel, palladium, or platinum, right? So you can also do that here. If you put an alkyne under the same condition, you will get reduction all the way down to the alkane. So you add molecular hydrogen twice. So in the first step, you add 1 pair of hydrogen in a cis fashion, but notice that you have an alkene now, and alkenes are quite reactive towards catalytic hydrogenation, so therefore it won't stop at this intermediate. So the reaction happens further until another pair of hydrogen is added over the alkene. Right? So if you wanted to do that, great, but this begs the question, what if I just wanted to stop at the alkene? Is that possible? And in fact, it is possible. So in order to stop the reaction from proceeding further and stopping at the alkene, what you need is known as a poisoned catalyst, meaning that this catalyst will catalyze the first step of hydrogenation, lowering the activation barrier of only the first addition of hydrogens, but not lowering the second step, so basically stopping at the alkene. So what are these poisoned catalysts? So there's 2 you need to know of. The first one is called Lindlar's catalyst. And basically, Lindlar's catalyst is when you have this palladium catalyst, but it's weakened a little bit. So you would also have in it quinoline and barium sulfate along with methanol. Or sometimes you can also see it as palladium with calcium carbonate and trace amounts of lead 4 oxide. In most cases, you will see it written as Lindlar's catalyst. The second one is known as a P2 catalyst, or written as nickel 2 boron, even though the subscript in actuality is nickel 2.5 to every 1 boron, but we will live with Ni2b for now. And that's when basically you add sodium borohydride to nickel acetate and ethanol. So both of these are considered poison catalysts that will stop at the cis alkene. Now if you wanted the trans alkene, you can also do it by adding the alkyne with sodium metal in liquid ammonia. Okay, so how does this mechanism work? This mechanism relies on radical chemistry, so we won't go into much detail because we haven't seen the radical chemistry chapter yet. But know that radical chemistry just means 1 electron is being involved. So when you draw the mechanism, instead of an arrow with 2 fishhooks, you will draw an arrow with only 1 fishhook representing movement of 1 electron at a time. So again, in this dissolving metal reduction, you take the advantage of the fact that sodium, the metal, loves to give electrons. So it's going to give away 1 electron to the alkyne. So that breaking 1 pi bond of the alkyne, where 1 electron combines with the 1 electron from the sodium, forming a pair of electron and therefore a negative charge there. And the other electron from that pi bond is resulted in a radical or a single electron on the other carbon of the alkyne. So because you are forming a radical and a lone pair, across this pi bond, you would want to favor a structure where both of these electron densities are far away from each other as possible to reduce any repulsion. So as seen here, if they resulted in a cis structure, there will be high repulsion between these two electron densities and therefore a higher energy profile. So instead, the intermediate goes through a lower energy profile, putting these two electron densities opposite face of each other, trans to each other. And this is what dictates the stereoselectivity of the trans product at the end. So once that's established, the lone pair grabs its first hydrogen from the liquid ammonia in a proton transfer step, giving this radical intermediate. So at this step, the sodium then donates another single electron, forming now a lone pair on this carbon, at which time then can go ahead and grab its second hydrogen, its second pronation step, forming your trans alkene. Okay, so to summarize all of this, if you simply submit it to hydrogen gas over a catalyst like palladium or platinum, you will simply get a full-on reduction to the alkane. However, if you want to stop it at the alkene in a cis fashion, you would use Lindlar's catalyst with hydrogen gas. Now, if you want the trans alkene, then you can add it with sodium metal in liquid ammonia. Okay, so let's do predicting products here. If you had this terminal alkyne, what would happen if you submitted to hydrogen gas and nickel? Hopefully you see that you do generate the alkane total reduction of all the pi bonds there. What happened if you do that with hydrogen gas again though, but this time with Lindlar's catalyst? What would you get? You would get the cis alkene, right? And then lastly, what happened if you submitted with sodium metal and liquid ammonia? Hopefully you see that you will get the trans form of the reduced alkene. Alright, so we'll end this video here for now and continue with the second part of alkyne chemistry in the next video.